Hello, this is Dr. Hanaa Assil, and this is the third part of the review on Modular Unit 1. This is in the IGCSE Chemistry Edexcel. So, let's start with metals. So, we talked about metals and we said the structure of a metal is made up of giant three-dimensional structure in which regular rows of positive ions are surrounded by a sea of free-moving delocalized electrons. And we said all metals conduct electricity because they have free-moving delocalized electrons. All metals are malleable and ductile because layers of positive ions can slide over each other when heated or hammered, and all metals are shiny. We said if we're comparing reactivities, any metal in group 1 is more reactive than group 2, group 2 is more reactive than group 3, and all of these are more reactive than transition metals. So the chemical reactivity series is actually showing the relative reactivities of the metals that are usually used. So we have potassium, sodium, calcium, magnesium, aluminium, and we put carbon and carbon monoxide here for a reason. We're going to use it when we talk about extraction of metals. And then zinc, iron, tin, and we have hydrogen in there because we're going to use it when talking about reaction with water or acid. And then everything below hydrogen, copper, silver, and gold. So we talked about why in group 1, for example, the reactivity increases as we go down the group. We said that reactivity of a metal has to do with how easily it loses its outermost electrons in order to have a full outer shell. So if it loses the outermost electron more easily, then it is more reactive as a metal. So which will lose the electron more easily, lithium or potassium? Remember that in potassium there are more shells, so the electron to be lost is further away from the nucleus, less attraction forces to the positive nucleus, so the electron is lost more easily. Metals, we know that all metals react with oxygen, and when they react with oxygen, they form the oxide. So sodium with oxygen would form sodium oxide, and these oxides are usually basic. So when I dissolve the oxide of sodium or any of the other common metals, dissolve in water, it gives the hydroxide, forming an alkaline solution due to the presence of hydroxide ions. So when magnesium burns in air, it reacts with oxygen to form magnesium oxide. And you should know that when magnesium burns, it burns with a bright flame or a white flame. And the magnesium oxide that is formed is a white solid, or we call it white ash. Some oxides of metals are amphoteric. Remember, amphoteric means they can act as both acids and alkalis. So oxide of aluminium, for example, can react with acid, so it forms the salt plus water, or it can also react with a base to form the aluminate. So the salt in that case is called sodium aluminate, for example, plus water. If we react with water, which of these will react with cold water and which one will react with steam? Now remember, the more reactive metals in group 1 and at the bottom of group 2, they react with cold water. And when a metal reacts with cold water, it gives hydroxide plus hydrogen. So other metals that are less reactive will not react with cold water easily, but they will react with steam. And when a metal reacts with steam, it gives the oxide plus hydrogen. Now, any metals below hydrogen in the reactivity series will not react with water or with acid because they are less reactive than hydrogen. So when potassium is placed in cold water, potassium of course is a very reactive metal, so it reacts with cold water, and we said when metals react with cold water they form hydroxide plus hydrogen. You should realize that all group 1 metals would float on the surface of the water. They have low density. They dart, they move around because the bubbles of hydrogen gas will push it around, and the piece of potassium metal will slowly melt or disappear. Potassium is very reactive, so we get very vigorous fizzing due to hydrogen gas, and the bubbles of hydrogen gas will catch fire. Remember that potassium, when it burns, it gives a lilac flame. Now, sodium is a little bit less reactive than potassium, but it is still very reactive, so it reacts with cold water to give sodium hydroxide plus hydrogen. Again, the sodium floats and darts. Again, we get vigorous fizzing. The other one was very vigorous. The solid again disappears, and here the bubbles of hydrogen gas may catch fire. Of course, the solution formed in all cases here is an alkaline solution, so if we have litmus or universal indicator, it turns blue. Calcium is also reactive, but it's less reactive than sodium. So here we have, in this case, calcium is in group 2, so heavier than water. It sinks. Strong fizzing. Do you see the difference? Very vigorous, vigorous, strong. And here it doesn't catch fire, of course, because the bubbles are underwater, and the solution becomes milky because the calcium hydroxide formed is not soluble in water. Magnesium. Now, magnesium is less reactive than the previous metals of group 1. So magnesium will react with steam, and we said when a metal reacts with steam, it forms oxide plus hydrogen. So this is magnesium oxide plus hydrogen. Again, remember, magnesium burns with a bright flame and a white solid is formed. Metals that are above hydrogen in the electrochemical series would react with acids. So magnesium, for example, will react with acid to give salt plus hydrogen gas. Now, magnesium is more reactive than zinc, so bubbles of hydrogen gas in the magnesium would be faster or more vigorous than in zinc. Anything below hydrogen in the electrochemical series does not react with acids. Displacement reactions. Remember, a more reactive metal would displace a less reactive metal. So zinc plus copper sulfate, for example, the copper sulfate is originally a blue solution. Now, when it reacts with the zinc, it forms zinc sulfate. That's a colorless solution. The piece of zinc dissolves, and when the zinc displaces the copper metal forms, and that is a red precipitate or a red solid, or we call it reddish brown solid is formed. Rusting of iron. This is corrosion with respect to iron. We call it rusting. Rusting means we're reacting the iron with water and oxygen. So iron needs both water and oxygen in order to rust. And when it rusts, it forms that reddish brown flaky substance. This is called hydrated iron 3 oxide. So remember that the chemical name for rust is hydrated iron 3 oxide. If we say what is the appearance of rust, it is reddish brown and it is flaky. Flaky means it can be peeled off easily. So if I want to write a word equation for rusting, I must say iron plus water plus oxygen. This gives rust, and we said the chemical name for rust is hydrated iron 3 oxide. We want to prevent rusting. We can use a barrier method. So painting of railings or painting of gates, the paint acts as a barrier to prevent iron from reacting with oxygen and water vapor in the air. So this is called a barrier method. Another barrier method is coating with oil. So if we have machines, we can coat it with oil or grease to prevent rusting. We have dishwashers or dish racks. We coat them with plastic. Again, this is a barrier method to prevent the reaction of iron with oxygen and water vapor in the air. But remember that for all of these methods, if the iron is exposed, it will rust. The better method would be galvanizing. Galvanizing means covering the iron with a layer of zinc by dipping or spraying. So iron pipes, for example, can be galvanized. So we cover the iron with a layer of zinc by dipping or spraying. In this case, the zinc is more reactive than the iron. And if any piece of iron is in contact with the zinc, even if some pieces of the zinc are peeled off, still the zinc is more reactive than iron, so it loses electrons and becomes oxidized instead of the iron. Sacrificial protection is when we put blocks of a more reactive metal strapped to the steel. So a more reactive metal like magnesium or zinc, we can put a piece of that metal strapped to a steel, such as in, remember steel is iron, an alloy of iron. So this is used, for example, to protect ships from rusting. This is called sacrificial protection. Again, the more reactive metal would lose electrons, become oxidized instead of the iron. So this is a common experiment to demonstrate rusting. So we have iron wool at the top there in the measuring cylinder, and at the beginning we have, of course, water. That means water vapor in the measuring cylinder, and we have air. That means oxygen. Now if we leave it for 1 week or 2 weeks, it starts to rust. It takes the oxygen that is in the air in order to rust, so the water goes up in the measuring cylinder to replace the oxygen that was used up in rusting. Now after 2 weeks, the iron has already rusted, so the water does not go up anymore. So explain these observations. Remember that at the beginning the iron reacted with oxygen in the air, so the volume of gas in the measuring cylinder decreased. Remember, I'm going to remind you that air is about 21% oxygen. After 2 weeks, all the oxygen in the air has been used up, no more reaction, so the volume of gas remains the same. What about oxidation-reduction reactions? You should remember definitions. Oxidation, if we're talking about oxygen, with respect to oxygen, oxidation is gain of oxygen, reduction is loss of oxygen. But usually we also talk about electrons. You should realize that oxidation is loss of electrons, reduction is gain of electrons. Another way of determining oxidation is the loss of hydrogen or gain of hydrogen. Gaining hydrogen is reduction. Another method is using oxidation number. Remember, oxidation number is the charge on the species or the valency that we talked about. So if the oxidation number increases, so I'm changing iron 2 to iron 3, that is oxidation. If the oxidation number decreases, for example, Na plus 1 that has an oxidation number of plus 1, now it changes to Na where there is no oxidation number, and that means the oxidation number is 0. So it's changing from plus 1 to 0, decreases, that's reduction. Iron 3 to iron 2, the oxidation number decreases, that is reduction. If we have both oxidation and reduction in the same equation, that is a redox reaction. So redox reactions involve both oxidation and reduction. So if we look at equation like this. What is happening? The copper oxide changed to copper. That means it lost oxygen. Loss of oxygen is reduction. The hydrogen gained oxygen to become H2O. That is oxidation. Or if we don't have oxygen, oxidation number of iron alone is 0. If it changes to +2, that means oxidation number increased. That's oxidation. Now the copper is changing from +2 to 0. Oxidation number decreases. That is reduction. Now remember that the substance that was reduced is called oxidizing agent. And examples of oxidizing agents are potassium permanganate, and you should know the colors. Potassium permanganate is purple. When it reacts, it becomes colorless. Or potassium dichromate, it's originally orange. When it reacts, it turns to green. Or halogens, because halogens tend to gain electrons. All of these are examples of oxidizing agents. So the oxidizing agent is the one that was reduced. The reducing agent is the one that was oxidized. So examples of reducing agents: hydrogen, carbon, which occurs in the form of coke, carbon monoxide, metals, because they tend to lose electrons and become oxidized. All of these are examples of reducing agents. So the one that was reduced is the oxidizing agent. The one that was oxidized is the reducing agent. Again, the one that was oxidized is reducing. The one that was reduced is oxidizing. Remember, oxidizing and reducing agents are reactants. We do not look at anything after the arrow. So if we have this, usually the question says, explain which element has been oxidized. So which of these has been oxidized? You can see that the carbon changed to carbon dioxide, gained oxygen, so that is the one that has been oxidized. Then we need to talk about extraction of metals. Remember, metals are extracted from their ore. The ore is the raw form of the metal obtained from the earth. So each of the metals we're going to talk about, you should know what was the ore, the raw form of the metal obtained from the earth. Now the method that we're going to use depends on which metal are we talking about. Are we talking about something very reactive? Because the very reactive metals, more reactive than carbon, will have to be extracted by electrolysis, because I cannot say carbon plus the oxides of any of these metals. So I can't say carbon plus magnesium oxide. It will not react because carbon is less reactive than magnesium. I cannot say carbon plus aluminium oxide because carbon is less reactive than aluminium and will not displace it. But metals that are below carbon, we don't need to use electrolysis because we can use it by or extract it by reduction with carbon, which is a cheaper method, so it is preferable to electrolysis. So when we want to extract aluminium, remember aluminium is more reactive than carbon, so we cannot extract it by reduction with carbon, so we need to use electrolysis. Now you have to remember that the ore of aluminium is bauxite. That is a hydrated form of aluminium oxide. So bauxite is the ore of aluminium. We first heat it, we get aluminium oxide, which may be referred to as alumina, and we need to do electrolysis. So we need to heat the aluminium oxide until it melts. We have to have free moving ions. Aluminium oxide is an ionic compound. If it's a solid, it does not conduct electricity. If it is molten, it would conduct electricity due to the presence of free moving ions. But the problem with aluminium oxide is that it melts at a very high temperature, 2100. So I need to add an impurity, which we call cryolite, in order to lower the melting point. So in this case, the cryolite that's added to the aluminium oxide is added to lower the melting point of the aluminum oxide and to act as a solvent. Electrodes, of course, are made of graphite, and we know that the ions present are aluminium 3+ and O2-. I'm doing molten aluminum oxide. So the aluminium ions go to the cathode because they are positively charged, so they go to the negatively charged cathode, gain electrons and become aluminium. At this high temperature, the aluminium is molten. Now the O2- goes to, these are negative ions. Remember, we said negative ions are called anions. They go to the anode, they lose electrons and become oxygen gas. But remember that the anode is originally made of graphite, which is carbon. So when we form oxygen gas at the carbon anode, the anode burns in the oxygen form to give carbon dioxide gas. So the two gases formed at the anode are oxygen and carbon dioxide, and the anode needs to be replaced from time to time because it burns in the oxygen form to give carbon dioxide gas. What do we use aluminium for, and what is the property that allows us to use it for that? So we use aluminium to make food containers. Why? Because it resists corrosion, it's not poisonous, it does not react with the food. We also use aluminium to make aircraft bodies. Again, why is that? Because aluminium is low density and it is strong to withstand pressure. We use them for overhead cables. So the overhead cables are made of aluminium. Why? Because aluminium has low density and it's a good conductor of electricity. We use aluminium for cooking utensils. Again, which property allows us to use it for that? It is good conductor of heat and does not react with the food, or it's not poisonous. Now, to extract iron, we don't need to do electrolysis because iron is less reactive than carbon. So it is extracted by reduction with coke. Coke is a form of carbon. This is because iron is less reactive than carbon and can be displaced by it. Now, this is done in a huge furnace called a blast furnace. So the apparatus in which this happens is actually a huge building called the blast furnace. Remember that the ore of iron is hematite. Hematite is Fe2O3. This is iron 3 oxide. So the ore of iron is hematite. We put into the blast furnace, we put the coke, limestone, which is calcium carbonate, and the hematite. We put that at the top, and below we put in hot air. So there is hot air coming from down, and the coke, limestone, and hematite going in. Then reactions happen. So the first reaction that happens is the coke, which is carbon, burns in air to give carbon dioxide. Now we know that when we burn coke, this is an exothermic reaction. So this helps to raise the temperature of the furnace. But then we still have a lot of coke, so the carbon dioxide formed is again reduced by coke to form carbon monoxide. And it is the carbon monoxide that acts as a reducing agent in the blast furnace. It reacts with the iron 3 oxide to give iron plus carbon dioxide gas. But we also put limestone into the blast furnace. Now, why did we put limestone? This is to remove impurities. Remember that the ore is something that's extracted from the earth. So it has a lot of sand or soil. That's the main impurity. The limestone, which is calcium carbonate, in the heat of the furnace breaks up to form calcium oxide plus carbon dioxide. You should realize that calcium oxide is a basic oxide. It reacts with silicon dioxide. This is oxide of a nonmetal. So these are acid plus base, and the salt formed is called calcium silicate or slag. And the slag floats on top of the iron. So in the blast furnace, the slag floats on top of the iron and it prevents its reoxidation. And then when we remove it from the blast furnace, it is used in rod making. The iron that comes out from the blast furnace is not pure. I can purify it by passing or bubbling hot oxygen through it. Now that oxygen will oxidize the main impurities like carbon to form carbon dioxide gas, sulfur to form sulfur dioxide gas, and these escape. And we add also calcium oxide, which is a base. The calcium oxide reacts with the acidic impurities formed and removes them in the form of slag, again that floats on top of the iron and is removed. And then we can make different types of steel. Remember, steel is iron plus something else, iron plus carbon, and maybe other metals like nickel and chromium, to adjust the different types of steel that we need to form. So we said steel is an alloy. Remember, alloys are mixtures of metals with other elements. Alloys are mixtures of metals with other elements. So they can be metal with metal or metal with non-metal. And that is formed by mixing the molten metals together and then allowing them to cool. So instead of having regular rows of positive ions, now we have atoms of different sizes or ions of different sizes. And that makes the alloy stronger and harder than the pure metals because the atoms of different sizes prevent the layers of positive ions from sliding over each other easily. So alloys are less malleable, less ductile than the pure metal. In addition, when we have alloys, alloys are more resistant to corrosion than the pure metals. So steel is an alloy of iron. So if it is just iron and carbon, it could be mild steel or high carbon steel. But if it has iron and carbon and other metals like chromium and nickel, that is what we call stainless steel. So you should remember that mild steel is used for car bodies and machinery. The high carbon steel is used in cutting tools and machinery. Stainless steel is used in making cutlery. Alloys of copper, if we have copper and zinc, that is called brass and it's used for ornaments or buttons. Alloys of copper and tin, that is called bronze, and it is used again for ornaments and for making coins. So remember, brass and bronze are alloys of copper with zinc or with tin. Let's talk about acids, bases, and salts. You remember definition. Acid is a proton donor. That means when I dissolve it in water, it forms H plus ions, which we refer to as proton, because actually H plus is something that has only a proton in the nucleus. The base is a proton acceptor. When we dissolve it in water, it forms hydroxide ions. That makes it alkaline, and the hydroxide ions accept protons, which reacts with H plus. So the hydroxide ion reacts with the proton, which is an H plus, to form water. You should remember, alkali is a base that dissolves in water, and when we react acids with bases, the substances that come out are called salts. So salts are ionic substances produced from reaction of acids with bases. Now, an acid or a base could either be concentrated or dilute. A concentrated substance has less water added to it, whether it's acid or base. A dilute acid or base has a lot of water added to it. How do we classify acids or bases? We use a pH range from 0 to 14. Anything that has a pH of 0 or 1 or 2 or 3, these are referred to as strong acids. So at a pH of hydrochloric or sulfuric or nitric would be somewhere between 0 and 3. Now, weak acids like vinegar, lemon, ethanoic acid, these have pHs of about 4, 5, or 6. Something that is neutral like water or salts will have a pH of 7. Something that is a weak base like ammonia has pH 8, 9, and 10. Strong bases will have pH between 11 and 14. Remember that definition of a strong acid is that it ionizes completely in solution to give lots of H plus ions. That means if I dissolve HCl, all the molecules will break up to form H plus and Cl minus. So we have a lot of H plus ions in solution, and we said the pH could be anywhere actually from 0 to 3. A weak acid ionizes partially to give less H plus ions. So all organic acids like ethanoic acid or citric acid, only some of the molecules will break up to form H plus ions. Its pH ranges between 4 and 6. A strong base again ionizes completely, but of course a base gives OH minus, and it will have pHs between about 12 to 14. A weak base like ammonia will ionize partially, so only some of it ionizes to give OH minus, and that means its pH is between 8 and 10. An indicator is a substance that has different colors in acids and bases. So we said the indicators we talk about are litmus, universal indicator, phenolphthalein, and methyl orange. Litmus paper will determine if something is an acid or a base. So if it's acid, the litmus turns red. If it's a base, the litmus turns blue. But if I want to know if it's a strong acid or a strong base or a weak acid or a weak base, we need to use universal indicator paper. So the universal indicator paper, if something is neutral, like water or salt, it has a green color. Anything below is acidic, but a strong acid will turn the universal indicator paper red, just like litmus. So HCl or sulfuric or nitric will turn the universal indicator paper red. A weak acid will turn it to orange or yellow, and bases will turn it to different shades of blue. Phenolphthalein and methyl orange are indicators that are used in titration. When I need a liquid indicator, I can either use phenolphthalein. If I put it in a base, it's pink. In neutral or acid, it's colorless. Or I could use methyl orange. Now, methyl orange, if I put it in a base, it's yellow. Neutral, it's orange. And in acid, it is red. What type of reactions can we have? We have acid plus base to give salt plus water. This is called a neutralization reaction. So if I have any acid, the acid has a very low pH, reacting with a base that has high pH. This will form a solution that has a pH of 7. That means I have neutralized the solution. So this is called neutralization reaction. So acid plus base gives salt plus water. Now, if I'm reacting acid with metal, it gives salt plus hydrogen. So any acid that is above hydrogen in the electrochemical series reacts with the acid to give salt plus hydrogen gas. Acid plus carbonates. Any carbonates will react with acid to give the salt plus carbon dioxide plus water. Remember that means that what we see is bubbles of gas or fizzing due to the formation of the carbon dioxide gas. Now, the base reacts with ammonium salts. So if I bring a base, sodium hydroxide or potassium hydroxide, with something that has ammonium, it gives ammonia gas, because this gives the salt plus ammonia plus water. Remember that ammonia is a base, so it reacts with acid, but it's a base that does not have OH. We said acid plus base should give salt plus water, but in case of ammonia, we don't form water because we don't have OH in the base. So ammonia plus acid gives the ammonium salt. Ammonia plus HCl gives ammonium chloride, ammonium nitrate, ammonium sulfate, ammonium phosphate. Remember that HCl is unique, hydrogen chloride. As a gas, it is a covalent compound called hydrogen chloride as a gas. But when we dissolve it in water, it ionizes. It forms H plus and Cl minus. Now it's not covalent, it is ionic, and this is called hydrochloric acid. Now, when it dissolves in organic solvents, anything that's not water, no acid is formed. So, of course, the HCl remains covalent and does not do any reactions of acids. Remember that when an acid or a metal or a non-metal reacts with oxygen, it forms oxide. Usually, the non-metal, when it reacts with oxygen, it gives acidic oxide. So carbon dioxide, nitrogen dioxide, and so on, these are acidic. That means if I dissolve them in water, they form acid. But some of them are neutral. So some oxides of non-metals are neutral. Neutral means they don't react with acids, they don't react with base. So carbon monoxide, nitrogen monoxide, and of course the oxide of hydrogen, which is H2O, all of these are neutral. Now, oxides of most metals are basic. Basic means they react only with acid. So oxides of group 1 or group 2 or copper and so on, these are basic. But there are some exceptions. Some of them are amphoteric. We said amphoteric means they can react with both acids and bases. So which oxides are amphoteric? You should remember it's the oxide of zinc, oxide of aluminium, and the oxide of lead. These are amphoteric, react with both acids and bases. Remember, acidic reacts with base. Basic react with acid. Amphoteric react with both. Neutral does not react with acid or base. We said the oxide of some metals are basic. That's because when we dissolve them in water, they form a base, like magnesium hydroxide. And oxides of non-metals are acidic. So if I dissolve carbon dioxide in water, it forms carbonic acid. Sulfur dioxide in water forms H2SO3. This is called sulfurous acid. But SO3, sulfur trioxide, plus water will give sulfuric acid. How do we prepare salts? The method depends on what is soluble and what is not soluble. You have to know what is soluble. You should remember all nitrates are soluble. They form aqueous solutions. Sodium, potassium, ammonium salts, all are soluble. All acids, of course, form aqueous solution. Now, there are some things we use a lot: barium chloride, magnesium chloride, calcium chloride. All of these are soluble. Copper sulfate is soluble. Most of the other things are not soluble, such as barium carbonate. Most of the carbonates are insoluble, so they are solids. Silver halide, silver chloride, silver bromide, silver iodide are insoluble. Lead halides, lead chloride, lead bromide, lead iodide, all of these are insoluble. Barium sulfate is insoluble. Copper oxide is insoluble. And of course, all metals do not dissolve in water. So the method we use to prepare a salt depends on what we're preparing, and we're preparing it from what. So if I'm starting with something soluble, and I'm trying to make soluble salt, I do the method called titration. if I'm trying to prepare something soluble, but I'm starting with an insoluble reactant, the method is neutralization. If I'm trying to make something that is insoluble, that is precipitation. So, when we're trying to make soluble products from soluble reactants, all of them soluble, we do titration. We do titration in order to determine exactly how much acid I should add to the base so that we do not add too much acid or too much base. I want the result to be my salt plus water only, no excess acid, no excess base. So first I need to do the titration to know exactly how much I should add. So to do the titration, what we do is place 25.0, that is exactly 25 centimeter cubed of the base, sodium hydroxide, in a flask using a pipette. And to that flask we add 3 drops of phenolphthalein. If you remember, phenolphthalein on a base turns pink. Then we add acid from the burette until the pink color turns colorless, because we said phenolphthalein in neutral is colorless. And we note the amount of acid used. So now I know how much acid I should add. We repeat. If I'm trying to make the salt, then I repeat by adding the required amount of acid to the same amount of sodium hydroxide, but without using indicator. Now I know that I have a solution of sodium chloride in water. I heat the solution to point of crystallization, cool, filter the crystals, wash with a few drops of distilled water, and dry between filter papers. You have to remember some precautions when doing a titration. First of all, the flask should be placed on a white tile or a white paper. And if he says why, this is to allow us to see the color change clearly. The flask also, as I add drop by drop, the flask should be swirled while adding the solution from the burette. And this is to mix the contents to make sure that all of it reacts. When we read a burette, or actually a pipette, the eyes should be on the same level as the bottom of the meniscus. So we are reading from the bottom of the meniscus, that is the reading of the volume. When we do titrations, when we're doing a titration and then we're doing another one, the burette should be rinsed. Rinsed means it should be washed. It should be washed with what? First, it should be washed with water to remove traces of any previous solution or to prevent contamination with previous solutions. And then I need to wash it with the solution I'm going to fill it with. Why? To remove water. I don't want water in the burette because that would change the concentration of the solution that I am filling it with. Once we do the titration, we don't do it just once. We need to do it more than once and take average results. Usually we repeat them until we get concordant results. Remember we said, what are concordant results? They are those within 0.2 centimeter cubed of each other. So the difference between each reading and the other should not be more than 0.2 centimeter cubed. So when we look at the results for this experiment, first titration, they found that they were going to use 21.8. Second titration, 21.5, 21.35, 21.4. So which ones are we going to use? We're going to choose the ones that are within 0.2 of each other. So the differences between each of these three readings are less than 0.2. So these 3 readings are called concordant. And when we try to calculate the average or the mean, we use only the concordant results. We ignore that first one because it is way off, so it's probably wrong. And we add the 3 that are concordant, divide by 3, that gives me the average volume for the acid. We can also use titration to determine which base is more concentrated. So we are told that oven cleaners are actually solutions of sodium hydroxide. plan an investigation to show which of the two different oven cleaners contains the more concentrated solution of sodium hydroxide. We can use titration because the oven cleaner is a solution of sodium hydroxide. So I can do titration of the first oven cleaner, determine how much acid I need, and then repeat again with the same amount of the other oven cleaner. And of course, the one that needs more acid is the more concentrated. So we explain in detail. Put 25.0 centimeter cubed of the first oven cleaner or the first solution of sodium hydroxide into a flask using a pipette. Add 3 drops phenolphthalein, the solution turns pink. Add acid from the burette until the pink color disappears. Note the volume of acid. Now, here we just want to compare between acids. We're not trying to prepare a salt. So we note the volume of acid used, repeat using the same volume but of the other alkali solution. The one that uses more acid is more concentrated. The other method that is used to prepare a salt is neutralization method. In this case, what we're starting with is a solid. We're starting with an insoluble base. We're going to react it with acid to give the soluble salt. So in this case, I'm trying to make copper sulfate. And what we do is we add the solid copper oxide. And you should know that copper oxide is actually a black powder. Using a spatula to 25 centimeter cubed of sulfuric acid in a beaker. Here we don't need it to be exact, so I can actually use a measuring cylinder to put the 25 centimeter cube sulfuric acid in the beaker, and we keep adding the solid copper oxide until excess solid remains in the beaker. That's how I know that my reaction has finished. So the reaction finishes, or the sulfuric acid all reacts if we add copper oxide and the excess solid remains at the bottom of the beaker. In that case, we filter to remove the excess copper oxide, and that is removed as a residue. And then we take the filtrate. Now the filtrate is the solution of copper sulfate. So we heat to point of crystallization, cool, filter the crystals. So now we have the crystals in the filtered paper. So this is a question that says malachite is an ore of copper containing copper carbonate and several other compounds that are insoluble in water. You are supplied with several pieces of malachite. These chemicals and items of apparatus, sulfuric acid, magnesium powder, and so on. Describe how you would use the chemicals and the apparatus to obtain a sample of copper from the malachite. The malachite is copper carbonate, and it is in pieces. He gives me a pestle and mortar, so the first thing I should do is crush the malachite in a mortar and pestle. Now we put the solid into a beaker. If we add excess sulfuric acid, the copper carbonate reacts with the sulfuric acid to form copper sulfate solution, which is actually a blue solution. So the solution becomes blue, and any insoluble solids remain at the bottom of the beaker. We get rid of the insoluble impurities and we take the copper sulfate solution. Now I need to change it to copper. That means I can add a more reactive metal like magnesium. If I react magnesium with copper sulfate solution, we said before the magnesium is more reactive than copper, it will displace it, and a copper metal, pieces of copper metal deposits. Now I can filter that mixture and get the copper as residue. The third method is precipitation, in which what we are trying to make is insoluble. So here, for example, we're trying to make silver chloride, which is solid. Now, I need two reactants that are soluble. So I need silver something that is soluble, and we said all nitrates are soluble. And I need something chloride that is soluble, and we said sodium compounds are all soluble. So what we just do is add the silver nitrate solution to sodium chloride solution, immediately we get a white precipitate of silver chloride. We filter that through a filter paper and funnel, wash the residue with a few drops of distilled water, dry the residue between filter papers. Okay, another topic that we need to talk about is energetics. Energetics has to do with delta H, or taking in or giving out of heat. We know that an exothermic reaction is a reaction that gives out heat. Now, it gives the reaction inside the solution is giving out heat to the solution, so the temperature of the solution increases and the reaction becomes hotter. And you should know that all combustion reactions or burning releases heat and are exothermic reactions. Now, endothermic reaction is a reaction that takes in heat. That means the reaction that is going on inside the solution is taking heat from the solution, so the temperature of the solution decreases, the reaction becomes colder. And we should remember that changing from solid to liquid to gas, all of these are endothermic reactions. Now, we will be required to draw one of two things. Either we're required to draw the reaction profile diagram. Profile diagram shows delta H and activation energy. Delta H is the change in energy from reactants to products. If it is an exothermic reaction, that means reactants give out some of their heat, and that means the products have lower energy than the reactants, so the delta H is negative. Now, where is the activation energy? It's from reactants to the top. Activation energy is the minimum amount of energy needed for the reaction to occur. So, showing activation energy, that is a reaction profile. But in many cases, we're just required to draw energy level. Energy level, you don't need to include energy of activation. You just show where the reactants are, where the products are. If it's exo, the products are lower energy. The delta H is from reactants to products, and it's a negative value. If it's an endothermic reaction, again, the delta H is the difference in energy from reactants to products. But in endo, the reactants took in energy. That means the products have higher energy than the reactants. And the delta H is a positive value. Where is the activation energy? Again, it's from reactants to the top. If this is the energy profile, if I want energy level, we just draw reactants and products, and usually we include what are the reactants and what are the products. And the delta H is again from reactants to products. How do we calculate delta H? We can calculate delta H from bond energies. Bond energy is the energy needed to break a bond. And you're usually given information about the amount of energy needed to break a bond. So in reactants, we're trying to break the bond, so it needs energy to break the bonds. But the bonds of products, when they are formed, they give out energy. So the difference between the energy needed to break the bonds in reactants and the energy released when products are formed, that determines whether the reaction is exo or endo. So remember that bond breaking is endothermic. You give it energy. The reaction takes in energy to break bonds. And bond formation is exothermic. So when bonds are formed in the product, this gives out energy. And the delta H is the bond enthalpies of reactants minus products. So we're given bond energies. To break the HH bond, I have 436. That means I am adding 436, I am adding 242, and then I'm forming two HCl bonds. Each of them will give out 431. So the two HCl bonds will give out 2 times 431, and the Delta H is the reactants minus the products. Overall, if the delta H is negative, we said that means the reaction is exothermic and heat is lost to the environment. So if we have this equation, we're trying to determine whether this reaction is exo or endo. Again, I have one N triple bond N, so that's 941, plus I have 3 HH bonds, minus how many NH bonds do I have? I have 2 ammonia, each ammonia has 3 NH bonds, so minus 6 times the 391. Overall, the reaction delta H is negative. That means reaction is exothermic. Heat is lost to the environment. And in all of these, we're given bond energies. We calculate the amount of energy taken in for reactants, energy given out in products, and it is reactants minus products. So the delta H overall is this value. That is to calculate from bond energies, but we have another method to calculate delta H. We can do a reaction, measure the initial temperature and the final temperature. These reactions, as we said, should be done in polystyrene cups because polystyrene is an insulator and will not allow heat loss to the environment. And then we say Q is equal to mc delta T. M is the mass of the solution, and remember we said the mass of the solution is the same as its volume. C is a constant, 4.18, times the difference in temperature, that is Q. Q is the total energy. If I divide it by number of moles, that is the delta H. So here, for example, we are adding magnesium to this amount and volume and concentration of copper sulfate. We are told that the temperature rises from 20 to 65. Calculate delta H. To calculate delta H, we get Q first. Q is mc delta T. Again, M is the mass of the solution, so it's 100 times 4.18 times temperature difference. What comes out is in joules. Usually we divide it by 1,000 to use it as kilojoules in the equation for delta H. So delta H is Q over N, so I need to get N. N for this solution is concentration times volume, so this is number of moles, and the delta H is Q over N. Now delta H must have a sign. Why did we say it's negative? Remember, temperature rises. That means it is exothermic. That means delta H is negative. Again, here we're told the student uses, when the student did this experiment, the student's value is usually less than the data book value. Now, why is it that when I do the experiment, my result is less than what it should be? Usually, loss of heat to the surroundings, or what I started with was... Okay, this is another type of question in which we use, for example, methanol to heat a certain amount of water, and we want to know what is Q. So Q again is mc delta T. M here is the mass of the water, not the mass of the methanol. So the mass of the water is 125, so the M is 125 times 4.2 times the temperature difference. What comes out is in joules, and then we are required to get the delta H for this reaction. Remember that the delta H is Q over N. Now the N is the N of the methanol. So we need to get the mass of the methanol, the number of moles of the methanol, and the delta H is Q over N. Again, this is a combustion. Heat is given off, so the delta H, and the temperature rises, so the delta H has to be a negative value. Do not forget to put a sign for delta H. And we're going to stop here and continue the last part of the modular unit 1 in the